Hi everyone, welcome to Lecture 2 of Differential Equations in Linear Algebra, which you could also call Continuous and Discrete Dynamical Systems. I said at the beginning of Lecture 1 that this is my favorite subject of all time, but I never said why. Part of the reason why is because it generates such beautiful pictures like this one that you see here. This is called the Lorentz attractor. It's an example of a more general phenomenon called strange attractors. Lorentz was a person who discovered this, I think, back in the early 1960s. Lorentz was a meteorologist and was trying to model the weather or maybe the climate and came up with an oversimplified model that was deterministic, differential equations, but generated beautiful pictures that had what's called chaotic behavior, which is sensitive dependence on initial conditions. If you've heard of the butterfly effect, it's related to that. The butterfly effect essentially says if a butterfly is flapping its wings in one part of the globe, that can affect the weather in another part of the globe, say 2 weeks later or something. Small changes in initial conditions can have drastic long-term changes in the end behavior. Is that really the case? Well, the math says it is. Okay, I'm not sure how the experimental evidence is on that, but that's certainly what the math says. So again, beautiful kinds of pictures, interesting kinds of behavior. That's why I like it. I also like how the pictures interact with the symbolic and abstract math. Lecture 2 has three main topics: exponential models, which we did talk about in Lecture 1 some, two separation of variables examples, which is our first kind of example where we will have to do some integrals, and the main linear algebra topic here for Lecture 2 is coordinate systems, just trying to get across the main idea of what's called changes in coordinates. Before we get to those three main topics, though, I want to review our purpose, what we're doing, what kinds of topics we're going to talk about, and I do want to show you a generalization of the harmonic oscillator example that I talked about in Lecture 1, really to a nonlinear oscillator, which is a pendulum swinging back and forth. Some more interesting kinds of things can happen with a pendulum than just a mass on a spring. So let's remind you of our main goal for the course. This is my description: to quantitatively and qualitatively model, describe, understand, and predict the behavior of various systems that change over time. Which is pretty much everything in the entire world, right? Pretty much everything changes. Hardly anything is very static, at least not in a real long run. I'll mention some examples of this in a minute, but let me just focus on the meaning of these things. Quantitatively, again, focuses on really formulas and numbers, numerical approximations. Qualitative focuses more on understanding, you might say, looking at graphs, trying to understand the graphs and describe them with words. And modeling and description is part of it. Understanding, we can fully understand the math. That doesn't necessarily mean you know how to apply it, though. That's really something that's harder. We will do our best to apply it in the situations that we consider. And then we make predictions, but we always have to test our predictions against reality. Model building, if you do it on the job, is always a process that's ongoing. You always have to tweak your models to try to make them better and better. How do we do it? I mentioned this last time as well. By working from local to global. The difference equations and the differential equations that we consider are local in nature. They're telling us something about some unknown functions near certain points in time, say. But we like global information. We'd like big picture information, like an entire graph or an entire formula, and describing what happens in the long run. The Infinity Principle by Steven Strogatz in the book Infinite Powers. I'll remind you of that again. Very, very good book. I'll put an Amazon link to it in the description below. I highly recommend it. It gives you a lot of ideas about the purposes of calculus and differential equations, because differential equations is just an extension of calculus. To shed light on any continuous shape, object, motion, process, or phenomenon, no matter how wild or complicated it may appear, reimagine it as an infinite series of simpler parts, analyze those, and then add the results back together. The word add is kind of the key word here to make sense of the original whole. Essentially, in one word, this is integration. Though it's good, it does not always involve integration. And in fact, in Lecture 1, we were integrating by guessing, really. We guessed the formulas in our examples in Lecture 1, and that's going to continue to some degree in this lecture, though we will do some actual integrals in this lecture. We're going to do our first couple examples with separation of variables. Before I go on to the next slide, let me remind you again of our main textbook, which I'll have a link to in the description below as well. Differential Equations by Blanchard, Devaney, and Hall is our main differential equations textbook. My blog, Infinity is Really Big, Pendulum.com has an online text for linear algebra that I call Visual Linear Algebra Online. Currently here in June of 2020, it's got 10 sections on linear algebra. I'm going to add more later in the summer. That's our main linear algebra text, and we're going to try to meld these things. If you're looking for a pure linear algebra text, I highly recommend this one by David Ley. It's a widely used book, and it's got a lot of cool applications, and it also, in my view, views the ideas of linear algebra in the best way. What are our main applications? Population growth and decay, that already came up in lecture 1, that'll continue here in lecture 2, including interacting species. Projectile motion, that's like up-down motion under gravity, but also of a projectile through the air in, say, a parabolic kind of path, with and without air resistance. Financial growth and flows, heating and cooling in the simplest kind of examples, mixing problems, where we're mixing salt water, say, and perhaps most importantly, harmonic oscillators of various forms, mechanical and electrical. Mechanical means physical oscillators like masses on springs. Electrical is, well, it's electricity, voltages, and currents. Undamped and damped. Again, undamped means no friction, damped means friction. Linear and nonlinear. The harmonic oscillator we talked about in lecture 1, a mass on a spring, is an example of a linear one. We can find formulas for solutions. I'm about to show you a nonlinear oscillator, that's the pendulum, where we can't actually find ordinary kinds of formulas for the solution, though you can essentially define new functions that would be new kinds of formulas. And then finally, forced and unforced, whether we have some sort of external forcing or not. All right, so here's an unforced, undamped, nonlinear pendulum. Okay, so it's an object swinging back and forth. The official name is it's a bob. Okay, that ball you say is a bob, and the black line there is a thin rod. For the sake of simplicity, you assume the black rod is massless. The only mass is in the bob itself. Of course, that's an oversimplification. The rod is going to have some mass to it. Under the influence of gravity, if you give it some initial angle and some initial angular velocity, theta is the angle, v is actually the angular velocity in radians per second. And by the way, we always use radians for the most part in here. Actually, there's one spot where we might use degrees. But for the most part, we use radians here. And so it is an oscillatory kind of motion here, back and forth, that you see here for this pendulum. So you might initially guess cosines and sines would be a good description of that, like they were for the mass in the spring. That description works pretty well if the angle is small. However, I've allowed this pendulum to have a large initial angle right there, almost 180 degrees, almost pi radians. In fact, I chose it to be 3 for theta. Very large angle, and because of that, when it's close to the peak, it sort of pauses longer than a typical harmonic oscillator would at its peak. It's not quite simple harmonic motion. It's a bit more complicated. It's nonlinear in nature. That's the actual motion here. What is this? This is the phase plane. Let me show you where I've got this in a Mathematica notebook here, where we can slow it down a bit and think about it a little bit more carefully. This is definitely worth doing. So here's some code that will run this, and also allow me to slow the animation down a bit. Slower here. And I want you to think about the physical interpretation of what's going on here in relation to both of these pictures. How are these pictures related to each other? This is one of the most important things to get out of the course, so make sure you're paying attention. So theta, again, is an angular variable. It's not really a distance traveled. What's keeping track of this blue angle that you see here? That's what theta is doing, in radians. So the initial angle is theta equals 3 radians, which is close to pi, close to 180 degrees, right up there. And theta's changing. The pendulum is swinging back and forth. No friction. If there were friction, the amplitude of the swinging would get smaller and smaller. What happens as the bob is moving to the left, as theta is decreasing? By the way, theta equals 0 is the downward. Theta is positive over here, and theta is negative over here. Okay? So let's say theta starts up here. By the way, in the animation, I let time both run forward and run backwards. Let's go ahead and actually it's not going forwards and backwards here, okay. when the pendulum is swinging in this direction, v is negative. The angular velocity is negative, like right now. In this picture, v is negative. You're down below this theta axis where v is negative. When the pendulum is swinging in the positive angular direction, the angular velocity is positive, like right now. You're up above the theta axis where v is positive. And you can see, if you think about the left-right motion of that red dot, that is keeping track of the angle itself. When the angle is positive, you're to the right of this right now. It's positive, positive. Now it's negative when you're over here. We're going to think about the acceleration of this as well. Let me do it right now, and then we'll go back to the PowerPoint, and I'll talk about it a bit more carefully. What's the acceleration, the angular acceleration of this thing? Well, it turns out that when theta is positive, when you are over here in this picture, the angular acceleration is negative. What does that mean? Well, like right now, it means you're slowing down. And once you start coming back down, like right now, it actually means you're speeding up when the angular acceleration is negative. Acceleration is directional, just like position and velocity are directional. So just because you say something has a negative acceleration doesn't mean it's slowing down. It is slowing down, again, right now, but the acceleration is still negative there because it's speeding up in the negative direction. That's really, really important to try to think about. Let's go back to the PowerPoint and I'll see how this plays out in the equations, in the differential equation. So it turns out that a differential equation for this pendulum, if you assume the mass of the bob is a certain number, and you assume the acceleration due to gravity is picked with certain units to make things simple, is this equation here. The second derivative of theta with respect to time twice, meaning essentially the angular acceleration in radians per second squared. We're not talking distance traveled per second squared, we're talking change in the angle per second squared, is negative sine theta. Now you know that sine theta is a positive quantity if theta is between 0 and pi radians. So because of the negative sign there, this is a negative quantity. The angular acceleration itself is negative if theta is between 0 and pi radians, which is exactly when you are over here on the right. Because again, that's theta equals 0 down there. Over here, theta is positive between 0 and pi. The acceleration has to be negative over there. On the other hand, if you're over here, the angle is between 0 and negative pi, 0 and negative 180 degrees. Sine of such an angle is negative. If you put a negative sign in front of that, you get a positive number. The angular acceleration is positive in that case. What makes this nonlinear? It's the fact that I've got a sine function in there, as opposed to, like with the harmonic oscillator in lecture 1, I had a negative constant times theta. Here I have negative sine theta. That's the nonlinearity. What are the initial conditions? Theta of 0 is 3. We start at this spot right there. And theta prime of 0, which is the angular velocity at time 0, is 0. We put the pendulum up here and we just let it go. It starts moving from rest. In a physics problem, you'd see that kind of phrase, from rest. What's the formula for the unique solution? There is no simple formula for it. Unless you decide you want to define a new kind of function, which people do, including in this situation. It's just a function here, being in a differential equations course, that you probably have never heard of before. Okay? We're not going to get into that. We can define a function that models this motion and where the angle and the angular velocity follow this kind of path. Okay? This is called a phase plane. At any moment in time, the red dot is in a certain spot. It's completely specifying the angular position and the angular velocity at that moment in time for the pendulum. That's called a phase plane. Really important for this class. To emphasize that the solution does not involve simple sines and cosines, we can graph theta and v as functions of time. Now, you didn't literally see time in that last picture. You just have to imagine it because the animation helps you imagine it. But in these graphs, now you see time explicitly in here on the axis that goes to the right here. The blue graph is the angle as a function of time. starts up at 3, decreases, becomes negative, goes down to negative 3, in fact, before it goes back up again. And the red graph is the angular velocity, the derivative of the angle with respect to time. Units for the blue one would be radians. Units for this one would be radians per second. So actually, it's not really best to draw them in the same graph, but we'll be okay with it here. You know, the blue one does look kind of like a cosine, but it is flatter near the peaks and the valleys than an actual cosine is. The red one definitely doesn't look like a negative sign, other than the fact that it goes negative, then becomes positive, then goes negative, then becomes positive again, over and over again. So these are not pure sines and cosines. They're new kinds of functions that we really just have to approximate with technology, really. All right, here's the first of our 3 main topics for this lecture. We want to review exponential growth and decay. That was the main examples we considered in lecture 1, both for difference equations and differential equations. For the discrete model, that's a difference equation. The kind of linear difference equation that we considered with initial values, so it's called an initial value problem, and the unique solution I'm going to write up here. Here was our general kind of difference equation right here. Pn plus 1 was some constant times Pn. For the examples from lecture 1, K was 2 when the bunny population doubled every month. And then we considered an example for you to work on where K was 3, where the bunny population tripled every month. By the way, like in lecture 1, we will pause for an example very soon for you to work on. You want to pause the video. This is a difference equation. Even though you don't see any differences in it, well, you could subtract this from both sides and then you'd see a difference. We'll see some other models where it's maybe a better reason to call it a difference equation in those models. It's telling us to find the next month or year's population, say, take the preceding one and multiply by some constant that, for example, could be 2 or 3, but it could be, 1.1 or 1.7 or 2.4 or whatever. The constant can be anything. I'm taking to be positive to model both growth and decay of positive quantities. As far as math goes, you could consider K to be negative. Then this would actually define a sequence that would bounce back and forth in sign, positive, negative, if you did so. But I'm restricting ourselves to ordinary kinds of applications, so I'm going to consider only K to be positive here. The initial value is P sub 0, or P naught for short. That is the starting population. For the bunny examples, it was 2. This is local information. Again, telling us the relationship between neighboring values of the PNs. What's the unique solution? This is global information. There's the unique solution. Pn equals P0 times K to the n. For any n, could be 10, could be 100, could be 1,000,000, you can just plug into this formula to find the population, say, at that time n. You don't have to keep using this formula over and over again. That's good, right? We want to have global kind of information about what's going on. How do you verify that it's a unique solution? This was one of the main symbolic things that I emphasized in lecture 1. I'm going to continue to emphasize it now here in lecture 2. How do you verify that that satisfies both the difference equation and the initial condition? You plug it into the left-hand side and the right-hand side, simplify, and see that you get the same thing. Say that again. This is so important. You take this function right there, function of n, a discrete function. We think of n as 0, 1, 2, 3, etc., non-negative integers. Plug it into the left-hand side of the difference equation. Find Pn plus 1, in other words. What does that mean? That means use this formula and replace the n with n plus 1. So I get P0 times K to the n plus 1. I like to write my K's in cursive. I hope you're okay with that. My lowercase k's, at least. There we go. There's the left-hand, what the left-hand side simplifies for that particular function. What about the right-hand side? Does it simplify to the same thing? If it does, then it's good. It's a solution. The right-hand side is K times Pn. Go ahead and substitute that in place of Pn. K times P0 times K to the n. Then simplify. This is a k to the first power. We can rearrange by the commutative property of multiplication, and we have a k to the n plus 1 power right there. And now we have a match. This matches this. That's what makes this a solution of the difference equation. And as I emphasized in lecture 1, you pick some other kind of function, it will not be a solution. Go ahead and check it. It won't work. These are the solutions that you get. I'm calling this a unique solution because I'm thinking of P0 as being constant. You could call it a general solution if you thought of P0 as being anything. But I'm trying to emphasize I'm thinking of P0 as being fixed. So I'm calling it a unique solution. What's the corresponding continuous model? Differential equation. And again, we can consider a linear differential equation. This equation is linear because, well, you just have a multiplication of a constant times a variable in a sense here. And these variables, both with the n subscript and the n plus 1 subscript, are to the first powers. There's no square roots, there's no squaring, there's no cubing, there's no signs in there. That's a linear difference equation. Here's a linear differential equation. Similar kind of thing, k times p on the right side. We got a derivative on the left side. Differential is essentially synonymous with derivative. Differential equations have to have derivatives in them of unknown functions. Okay? This is talking about a discrete change. From time n to time n plus 1, you multiply by k. Differential equations are telling you about rates of change. The rate of change of the population with respect to time, the instantaneous rate of change, in fact, is k times the current population. Okay? For the example from lecture 1, one of the examples at least, k was natural log of 2, which was about 0.693, and that represented 69.3% growth as a relative growth rate. That occurs at every moment in time. I'll talk about what that means with a decay example here in a minute. The initial value is p of 0, which is p sub 0. Okay? You don't put subscripts on these p's. We're thinking of p as a function of t with ordinary function notation, p of t. The n up here is the input for this function, this discrete function. The t right there is the input for this continuous function. I'm thinking of n as being a positive integer, 0, 1, 2, 3, etc. I'm thinking of t as being a positive real number, or non-negative, greater than or equal to 0. What's the solution to that? I'm looking, here's something really important, pay attention to. I'm looking for a function whose derivative is k times itself. That's what the differential equation is saying to you, if you imagine it to be talking. Give me a function whose derivative is always, for all t, even though you don't see a t on the right-hand side here. It's k times the function, k times itself. You need to imagine there being a t there, but there's a good reason to not explicitly write it, okay, which we'll get to. Lots of strange little subtleties in this subject. It's one of the things that people have the hardest time getting used to, is all these strange little subtleties. The unique solution, if we imagine P0 is fixed, is this. P of t is P sub 0 times E. Yes, that's the number E. 2.718281828, blah, blah, blah. By the way, when people say 2.718281828 makes you think it's repeating. Does the 1828 keep repeating? No, it actually doesn't, although it does it first. E is an irrational number. It's not rational. And you think, again, of t as being a continuous variable, taking on real values. How do you verify that this is a solution? Same kind of idea. Take the left-hand side, plug in the function. In other words, find its derivative. I'll just write it y as y prime, or p prime, I guess I should say. P prime. Take the derivative for that function, not some other function. So by the chain rule, I get an extra factor of k, where I take the derivative of the inside function here. It's a composition. Kt, k times t is the inside function. P0 times e to the, call it x, is the outside function. Chain rule says take the derivative of the outside, which is this, plug in the inside, which is k times t, then multiply times the derivative of the inside. K is a constant. The derivative of this with respect to t is just k. What about the right-hand side? Kp. And again, even though you don't see a t there, You're imagining P depends on T. Now go ahead and plug that function in to get K times P0 e to the kt. Now I put parentheses in there for emphasis that that is the function P, but look, I can switch around where the K is. These two things are the same. That verifies this is a solution. And if I think of P0 as fixed, it's a unique solution for that fixed P0. If I think of P0 as arbitrary, then I call it a general solution, and it really would represent infinitely many solutions in that case. Okay? You pick some other function that can't be put in that form, it won't work. Try it. It won't solve the differential equation. You simplify the left and right hand sides, you will not get two things that are equal for all t. All right, let's summarize some things here. This is pretty important to know. And the summary that I'm giving here does generalize a lot to higher dimensional problems, and that's part of linear algebra as well, as helping us think about higher dimensional problems. Exponential growth and decay, descriptions and predictions. Summarize what's happened. With the discrete model, the difference equation, we really see that when k is bigger than 1, it's exponential growth. When k is between 0 and 1, it's exponential decay. And when k equals 1, it's static, it's constant. Why? Well, think about the formula for the solution. Pn was P0 times k to the n. If k is bigger than 1, like 2 or 3 or 4, that's growth. Even if k is barely bigger than 1, 1.00000001, it's still going to be growth. And it's still, in fact, exponential growth. It'll seem to grow pretty slowly at first, but actually if you go out far enough, it'll still grow pretty fast. If k is between 0 and 1, like 0.5, 0.5 to the n, as n gets bigger, gets smaller and smaller, right? 0.5 squared is 0.25. 0.5 cubed is 0.125. 0.5 to the 4th power is 0.0625, I think, yeah. So it keeps getting smaller and smaller if k is between 0 and 1. And again, I'm only considering when k is positive here. If k equals 1, then I get 1 to the n, which is always 1. Static. Pn always equals P0 in that case. For the continuous model, the differential equation, it is different. We have exponential growth if k is positive. And by the way, I don't know if you noticed there in the differential equation, I actually was allowing k to be negative in that case. I didn't say k had to be positive. It's exponential growth if k is positive. The formula for the solution is P of t equals P0 e to the kt. If k is positive, that's e to a non-negative power when t is non-negative. That keeps getting bigger and bigger as t grows. That is a k there, I'm sorry, the smartboard is not allowing me to write it completely. On the other hand, if k is negative, that's exponential decay. E to the negative t, for example, is still positive in value, but it's decaying in value, it's going down. And it's static if k is 0. If k is 0 here, you have e to the 0, which is 1 for all t. P of t equals P0 in that case, times 1, just P0. So it's similar but different. So make sure you're remembering this kind of distinction between the discrete and continuous model. Again, the main focus on this class is on the continuous model, but we will talk about discrete models, partially because it's nice to do with linear algebra, partially because it's in some ways simpler to think about, and partially because it actually will help us, I think about some higher dimensional situations as well, and it'll help us think about Euler's method for the numerical approximations. All right, your turn. Problem-solving practice with exponential models. So here's where you're going to want to pause the video. My students, you definitely should pause the video if you happen to be watching it here. We might meet in person. I don't know. It depends on how things are with the coronavirus. A car that is initially bought for $25,000 depreciates, loses value over time. So I said one application for us was financial growth and flows. I mentioned in lecture 1 that could be interest earned on bank accounts, maybe including when you keep putting in money in a bank account. This still could be thought of as a financial problem for certain. It's not financial growth, it's financial loss. I hope you know that your car loses value the second you drive it off the lot. Pretty fast, in fact, the second you drive it off the lot. It like goes down by 1,000 or 2 sometimes, right the second after you drive it off the lot when you buy a new car. Because people say, well, then it's used, in spite of the fact that, you know, they have loaner cars and cars that are being test driven, and then they say it's still new. Okay, that's just a little complaint about car sales. So here's the first situation. Use a discrete model, a difference equation, to describe the decay in value, assuming that it loses value at a constant relative rate of 25% per year. At what whole number age will it finally go under $1,000 in value? Okay, so this is discrete. When you pause the video and think about this, you want to think about n being discrete. 0, then 1, then 2, then 3, etc. Not continuous. That's the difference between discrete and continuous math. And you are thinking about price changes over an entire year in that case. Situation 2 is similar, except we're using a continuous model, a differential equation, to describe the decay in value, assuming it loses value, and assuming at every instant in time it's a continuous relative rate of 25% per year. These are rates of decay. Key word here in both cases, decay. The graphs are going to be decreasing. So, pause the video, see if you can figure out both the answers to both of these problems. You will ultimately need to use some logarithms like we did in lecture 1. All right, so let's come back and look at the answers to these things. This is a bit different than what happened in lecture 1 when we were talking about the doubling and tripling. The formulas in both the discrete and continuous case were really the same formulas essentially for lecture 1. P0 2 to the t for doubling and P0 3 to the t for tripling. Whether you use t or n, in fact, though we did relate it to e for the continuous one. This is really different though. 25% actual decay over an entire year is really different than a continuous decay rate, an instantaneous decay rate of 25%. So you get different answers. So here we go. Here's our difference equation. That's our discrete model. Where does the 0.75 come from? That comes from the fact that the loses value is at 25% per year. So at the end of any given year, it's 75% of the value of the preceding year. You know, we're talking about P0 being 25,000. I need to multiply that by 0.75 to find P1. I'll just go ahead and do it on my calculator here. 25,000 times 0.75 is 18,750. That's P1. P2, I need to multiply by 0.75 again. And you get 14,062.50. Losing 25% in value every year means the next year's value is 75% of the previous year's value. So you don't put a 0.25 there, you put a 0.75. You need to put something different for the differential equation. I hope you did that. There's the initial condition. Here's our solution. P0 times k to the n. K is 0.75, which is less than 1. It's between 0 and 1. This is decay. This is going down in time. 0.75 to the first, 0.75 squared, 0.75 cubed, keeps getting smaller and smaller. We want to set this equal to 1,000 to answer the question, solve for n, and we're going to round up at the end. You should round up, because we're talking about whole numbers answers in when it finally goes under 1,000. We want to look for one where it's under 1,000. Divide both sides by 25,000. Take the natural log of both sides and use a property of logarithms right there. That this, if I take the natural log of this thing, the n in the exponent can come in front as an n times the natural log of 0.75. I hope you know that natural log of 1/25 is the same as negative natural log of 25. That's a property of logs as well that you should know. Solve for n by dividing both sides by the natural log of 0.75, which, by the way, happens to be a negative number. And so the negative signs will cancel in the final computation, even though you still see a negative sign there, to give us a positive answer that you should check, about 11.2. So now round up to 12 years as the first year, when it's going to be under $1,000 in value. The differential equation is probably trickier. It's a 25% decay rate. That's an instantaneous decay rate. Continuous relative rate, 25%. So here you actually use 0.25, but with a negative sign. There's your differential equation right there. Does that make sense? Remember, it is decay. Looking like that. It's going to be an exponential decay. Or after the slope of that here, dp dt is the slope, it's got to be negative. What this is saying is it's negative 0.25 times whatever p happens to be at the time you're thinking about. So for an arbitrary time t, there's a certain price for the car. At that, whatever p happens to be at that moment in time, multiply it by negative 0.25, and that tells you the slope of the tangent line. It's negative 0.25 times p. Why not negative 0.75 times p? Well, I think it's probably because of the way this is just described. We could think about particular values if you want. I think I'm not going to get into that at the moment. Solve it. Guess, based on what I've said before, p of t is 25,000 e to the negative 0.25 t. Is this going to decay by 25% over the entire year? No, it will not. That 25% is telling you at any moment in time how much the tangent line is decaying. If this is t, and this is t plus 1 right there, the change, the relative amount of change in the tangent line is what the 25% refers to. The graph of the actual decay, because it's exponential decay, is concave up. So the actual decay, right there, is not as much. This is not going to decay as fast as this one did. And so it's going to go under 1,000 later than 11.2 years, later than 12 years, though not much later, it turns out. I think the answer is about 12.8 years. Solve for t, set it equal to 1,000, solve for t with logarithms. And of course, ln and e cancel to give you just negative 0.25 t there. Once again, natural log of 1 over 25 is negative natural log of 25. Divide both sides by negative 0.25. In other words, multiply both sides by negative 4. And t is 4 natural log of 25, which is about 12.88 years. Okay? So the language of how these things is phrased is important. So you need to make sure you pay attention to it. How would you figure out how much it decays every year? You could just compute e to the negative 0.25 and then subtract that from 1 essentially and convert it to a percent. E to the negative 0.25 is about 0.778. Subtract that from 1, you get about 0.7788. You get 0.2212. 0.2212, if I didn't make a mistake there. So that's 22.12%. A continuous decay rate of 25% per year is an actual amount of decay that's 22.12%. Okay, so again, pay attention to the language, the way things are phrased. What if we had a hard time guessing the answer? This is on to the second main part of lecture 2. So the first main part was looking at exponential models again. The second main part here is separation of variables, where we will actually do some integrals. We could solve by using separation of variables. Now for this kind of example, dy dt, we are talking about a differential equation here, dy dt equals k times y, or dp dt equals k times p. You can find the solution by guessing, by using the special property of the exponential functions in the chain rule. Here, however, I am going to emphasize we could also use this technique of separation of variables, which is more general and allows you to solve in situations where you may not be able to guess. So here's the differential equation. dp dt equals k times p. K is a constant. P is the dependent variable, the population or the price. T is the independent variable. The goal, remember the goal is to solve for p as a function of t. What you want to do first is pretend that this is a fraction here. Now you may have had a calculus teacher who said, don't, it's not a fraction. But here I say do, pretend it's a fraction because it gets you to the right answer. Is that allowed? Well, many people do it. They don't worry about whether it's really allowed or not because they know it gets them to the right answer, or it can if they don't make a mistake. I will justify this more in lecture 3, what I'm about to show you. It'll be a more rigorous justification. Pretend this is a fraction and try to separate the variables and don't worry about where the constant is. Get all the p's on one side and all the t's on the other side. That's separating variables. What about the d's? Well, the d's kind of just come together. dp is something that's involving p, and dt is something that's involving t. So I'm going to divide, I want all the p's on the left side, say, and all the t's on the right. I'm going to divide both sides by p to cancel it on the right, and quote-unquote multiply both sides by dt to cancel it on the left and make it appear on the right. That's separating variables. It's hand-wavy, like, does it really work? Is that really allowed? There's what it looks like if we do it. I divided both sides by p, and I quote-unquote multiplied both sides by dt. Again, I'll justify this more in lecture 3. When you see something like this, you should feel a great temptation to integrate it. It's almost like your hands start shaking, your arms start shaking. Must integrate, and so you go ahead and integrate, and then you feel better. Is that always a good idea? Usually, I won't worry about when it might not be a good idea. Integrating the right one is easy. That's a constant. You're going to get k times t plus a constant. Call that constant c1, say. Integrating this means really integrating 1 over p. Sometimes written like that is dp over p. If you integrate that, it's going to involve the natural logarithm, right? Calling it c1 instead of c, because we're going to have other c's involved. If I integrate this thing to get a natural log of the absolute value p, I'd have another constant that I could call c2. But if I've got constants on both sides, I might as well just subtract it from the left side and get just the constant on one side. And actually, I meant to put a c2 there, but I didn't. Okay. I can pretend that's a c2. The next one's going to involve a c2 that really should be a c3. Because the c2 here would really be like c1 minus whatever was on the left side. It's not a real big deal. Don't worry about it. We're going to get the right answer anyway. What's the goal again? Don't forget the goal. I want to solve for p. I don't like that natural log there. How can I get rid of it? Exponentiate. If these two things are equal, then these two things would be equal. By the way, that is the logic behind what we're doing. We're assuming we've got a solution and we're wondering what it would be. We're assuming there is a solution and we're wondering what the solution would be. These calculations don't actually prove what we get in the end is a solution. The left-hand side, right-hand side stuff is what you would really need for that. On the right side here, e to this kt plus c1 could be separated out by properties of exponents as e to the kt times e to the c1. Like that, right there. And then e to the c1 I could call c2. Okay, I probably should have had a c2 here, and this will be c3. Don't worry about it. I don't like the absolute value signs. What should I do with those? How about just get rid of them? Sure, why not? Get rid of the absolute value signs. Is that allowed? It's allowed because this works. This is the answer. You can check it. Or this is, if we assume there's a solution, then it's got to be of this form, essentially, is the logic again. To really prove it's a solution, You got to do the left-hand side, right-hand side stuff, which I won't bother with it. You can do it. We've done examples like this already. Get an extra factor of k when you differentiate it for the left-hand side. And for the right-hand side, you already are multiplying it by k. Here I'm abusing notation a bit. I'm treating the p as both a variable and a function name. That is a common thing to do, and that's what this book does all the time. Starting in lecture maybe 3, maybe 4, I will try to bring some clarity to this and say that abuse of notation, while we typically ignore it, is technically not ideal. It's technically not good to use the same letter for both a variable name and a function name. And I will use a new letter for the function name. It'll actually be a Greek letter called phi, which is a common thing to use. That's called a general solution of just the differential equation. C is arbitrary here, not something fixed. This is an infinite family of solutions. Any C will work. However, if I specify the initial condition to be some fixed number, P0, then C in fact has to equal P0, and I can write the unique solution of the IVP in the form that we've seen before. Okay? But to prove it really is a solution, you have to do the left-hand side, right-hand side checking. Checking is more than just making sure you did it right. It really is necessary in the logic of proving you have a solution. All right. Let's do another separation of variables example, where it's not so easy to guess. Here we again have an initial value problem. dy dt, going to y now instead of p. Y will be the usual dependent variable that we use. Equals t times y squared. Now I do have a t on the right-hand side, whereas before there was no t. There, as a product being multiplied, a factor being multiplied by y squared. Should I see a y of t quantity squared there? No, don't put the independence on t explicitly in the differential equation. And there's a really good reason for that, which we'll see pretty soon, lecture 3, 4, or 5, something like that. We'll see why it's a good idea to not explicitly put the y of t in there, even though in your mind you're remembering y does depend on t. And y of 0 is 4. So can I separate variables here? Yeah. This right-hand side is a product of something that just involving t with something just involving y. This is one good reason why not to include the t, in fact, in there. Divide both sides by y squared, and quote-unquote multiply both sides by dt. What happens when you do so? You get this. And once again, those are things that look like you should integrate them, right? These are sometimes called differential forms. You feel tempted to integrate them, and that's usually a good idea, and it is a good idea here. Integrate both sides. As before, the right-hand side is easy to integrate. That's not always the case. The left-hand side here is pretty easy to integrate too, but let's just do the right side first. Integrate t. With respect to t, you'll get 1/2 t squared plus a constant. Integrate y to the negative 2. Maybe you want to try that, pause the video and try that on your own. You'll get another constant that we can absorb into this, and I think if I made the C1 mistake with the last one, I probably made it with this one too. Oh no, I called it C2 now. Okay. So C2 is essentially C1 minus whatever constant I had on the left side. And when you integrate y to the negative 2, you will get negative y to the negative 1. Same as negative 1 over y. That's worth mentioning. This is the same as negative 1 over y. And then remember what the goal is. The goal is to solve for y. Okay, I probably don't want the negative sign there, so I multiply both sides by negative 1 to get rid of that negative sign, and I guess I'd have a negative sign there in front of the 1/2 t squared, and I guess I'd have a minus C2. C2 is an arbitrary constant, positive or negative. If I write that as minus C2, I could just change it and write plus C3. And that's what I did here. And I did that on another step is I took the reciprocal of both sides. 1 over y, when you flip it, becomes just a y. Negative 1/2 t squared plus C3, when I flip it, gives me this. Not this. Don't ever make that mistake. Oh, and why is this line missing? I thought I would put it there. Okay, that line should be there. These are not equal. don't ever think that they're equal, okay? If you're going to simplify this difference into two fractions, you'd have to get a common denominator, which would be the product of those two denominators. It would not equal that. It's so bad, I don't even want it up there with an X through it. I want to erase it. Okay. That's fine. You can leave the answer like that. I went ahead and made it a little simpler looking by multiplying both the top and the bottom by 2 to get a 2 up top. 2 times 1/2 is 1, and you still have the negative sign right there. C here is essentially 2 times C3. Here's your general solution. Now actually, this is not quite as an ideal general solution as our other example. Ideally, you want general solutions where, again, C is arbitrary here. C can be anything positive or negative or even 0. And it's going to give you a solution. However, it's not ideal because this actually misses one solution. There's one solution of this differential equation for a certain initial condition that this function will not allow you to find. That solution is the constant function y equals 0. That constant function is a solution of the differential equation because its derivative is always 0. And its y-coordinate's always 0. So the right-hand side is always 0 as well for all t. But there's no choice of c here that's going to make this function equal 0 for all t. So you could call it a general solution, but just realize in your mind it's not quite ideal. What about the initial condition, y of 0 equals 4? We've got to solve for c. Plug in t equals 0 and y equals 4. Get 4 equals 2 over c, which means c is 2/4 or 1/2. And the unique solution is this, where I plug in c equals 1/2 right there. And then that can be simplified yet a little further. Multiply the top and the bottom by 2. 2 times 2 is 4. 2 times 1/2 is 1. And then you get a minus 2 times t squared. Interesting thing to note here with this solution is this is actually faster growth than exponential growth. If you graph this function for positive values of t, it's got a vertical asymptote. In fact, quite quickly it reaches a vertical asymptote like that. That's supposed to be a dashed line there. At wherever the bottom is 0, 1 minus 2t squared equals 0. Means 2t squared is 1, t squared is 1/2. T is, if we want that vertical asymptote, the square root of 1/2. Same as 1 over square root of 2, same as square root of 2 over 2, which is about 0.707 is where the vertical asymptote is. This grows very, very rapidly when t is positive. It blows up, in fact, you might even say. There's no obvious reason in the differential equation why that should happen. That's something to be aware of. Differential equations can blow up in finite time. Now, you might be tempted to say, well, doesn't it come back from infinity? Can I graph it when t is bigger than that as well? Yes, you can graph it there, and it's technically a solution there. However, when we're thinking about particular initial value problems, if a solution blows up, we sort of want to ignore the part to the right of the vertical asymptote there. It's not really relevant if this were relevant for a physical model. Though if it were relevant for a physical model, you'd be saying, yikes, the model is blowing up or something. There may be no real-life situation that this is a good model for. Okay. All right, take a breath. And I need a drink of water here. We're going to transition to linear algebra. This is our third main topic for this lecture. I'll be doing it in time. I want to finish within 15 minutes here. All right. I will often maybe split these lectures into 2 or 3 parts. I'm not positive about that, but it might work out better here. But here initially we're doing entire lectures that themselves have parts. What's analytic geometry? It's what you might call a marriage between algebra and geometry. Historically speaking, you go back over a couple thousand years ago to ancient Greece. The Greeks like to think about whole numbers and geometry. They didn't have any algebra that they used, though they did arithmetic. don't know what their number system was like. It probably is not as handy as the Hindu Arabic system that we use today. There are reasons they were kind of suspect of algebra and arithmetic as well when they dealt with irrational. They were the first to discover irrational quantities, and that they didn't like that. Algebra was created by some Arab mathematicians, I believe, back in maybe around 800 AD or so. That's symbolic, right? Using symbols to represent numbers. And actually, the symbols many people used then weren't just individual letters, but maybe words. It was only in the maybe 1500s or so that people started using letters, X, Y, etc. Yeah, it's facilitated by the twin ideas of variables and coordinates. We're combining these things, and this gives us new insight into both algebra and geometry. That's the great thing about it. We've got a coordinate plane, like this. Right? Graph paper, essentially. By the way, you'll find a lot of these pictures that I'm going to show you on my blog. Infinity is really big in the linear algebra book, Visual Linear Algebra Online. The first section is about this stuff. This is something you know from, I don't know, 7th or 8th grade, right? Don't fall asleep on me here. Don't stop the video. There are going to be a lot of subtleties to pay attention to. It's worth your time to listen. What do you have here? Okay, so initially you imagine a plane, just a two-dimensional flat surface that you really literally imagine going on forever and ever in every direction. And then you impose a coordinate system, and the standard way to do it with rectangular or Cartesian coordinates is to make a horizontal axis that is literally horizontal and typically label it with an X, and a vertical axis that really is vertical and typically label it with a Y, though you don't have to use X and Y. And you can mark off unit lengths, 1 unit of length along each axis, and you typically, ideally, make these the same scales on both axes, though I mentioned in lecture 1 they don't have to be, and there's good reasons sometimes not to make them the same. And then you can draw these coordinate lines, this grid in here that makes it look like graph paper, to help you think about the coordinates of points. So P is this point right here. What are its coordinates? There's two ways to think about it. You see the vertical and horizontal dashed red lines through P. Where the vertical one touches the x-axis, that is its x-coordinate or first coordinate, and it's about 4.2, say. And where this horizontal line crosses the vertical axis, the y-axis in that case, that is its second coordinate, its y-coordinate, and it looks like it's about negative 2.8. So this ordered pair, 4.2 comma negative 2.8, is the coordinates of the point P. Another way to think about the coordinates is that these numbers here represent signed distances, signed, S-I-G-N-E-D. 4.2 is the signed distance of this point from the vertical axis. It's 4.2, that's the distance of this line segment right there, and it's a positive distance because you're to the right of the vertical axis. Whereas the negative 2.8 here is the signed distance of this line segment. It's 2.8 units long, but it's below the x-axis, so we call it a negative 2.8 signed distance. Signed, E here, by the way, signed. Coordinates of Q, looks like about 6.8, 4.5 or so. Coordinates of R, negative 6.4 or so, comma 8. Okay? When we change coordinate systems, the coordinates of the same points could be different. Different numbers to describe their address, the address of the points, the location. That's the first subtle point to make. Let's talk briefly about some applications. I'm going to go pretty quick here because we're running low on time. Applications of coordinate planes. Plotting a solution is a parametric curve. The point-valued function, this thing, is a solution of a linear system of differential equations. Have you ever heard of a point value function? This function of t takes t as input and gives you a point, an ordered pair, as output, that we could interpret graphically in a rectangular coordinate system. And as t changes, the point is going to change. It's going to move, motion, that we're modeling here. What's the system of differential equations it's a solution to? It's this system, dy dt equals v, dv dt equals negative 4y. Check this. We got two equations to check here. They both have a left-hand side and a right-hand side. dy dt, the left-hand side of the first equation, I need to differentiate y of t equals cos t to get negative 2 sine t. Sine 2t, excuse me, by the chain rule. But wait, hey, that's the same as this. That equals v for all t. For all t. Very important to emphasize this is true for all t. What about the left-hand side and the right-hand side of the second equation? And by the way, this is the right-hand side of the first equation. Sort of doing it all in one step here on each line instead of separating it into two steps. dv dt, differentiate v. Differentiate negative 2 sine 2t. I'm going to get negative 4 cos 2t. And that does, this thing here equals y. So this is negative 4y. This is true for all t. That checks that this is a solution of this system of differential equations. Both equations need to be true along a solution curve. All right, so that checks it. This should feel a little familiar if you watched lecture 1. This was our harmonic oscillator mass in a spring example. The differential equation in that case was a second order equation. Y double prime was negative 4y. V prime is the same as y double prime. It's the same example essentially, except I'm thinking of it as a system of differential equations first order instead of one single second order differential equation. When I say first order, I mean first derivatives. Second order equations involve second derivatives. The resulting graph of this parametric curve, let's call it a parametric curve, and it's defined by these equations in the parameter t. Why use the word parameter? I don't know. It is a variable still. There's what it looks like. Which I was gonna plot some points first, but we're running low on time. There's what it looks like. It's this blue oval here. The red dot is the location of the point as t varies, and you can see t varying up here. I use capital T here just because in my Mathematica programming that is the way it works out. This is the same as little t. So you see y and v changing over time. This is very analogous to the pendulum example we talked about, except now we're talking about a mass in a spring. And the formulas are known in this case. Ordinary kinds of functions you're used to. What are these red and blue vectors in here? Arrows in here. They're vectors. Starting in lecture 3, we're going to start talking some about vectors that will continue. What are vectors? They're arrows. The arrows have lengths and directions. The blue arrow is called the position vector of the point. It points from the origin to the red dot. And the red vector is called the velocity vector. Is it the same as this? That's a velocity, isn't it? Yes, this is a velocity for the mass in a spring up here. It's not the same as the velocity vector, however. So don't get confused about that. This velocity vector is just a velocity vector for the picture. It's related to the mass in the spring, but it's not equal to the velocity of the mass in the spring as it moves up and down. Another application, finding and plotting what are called equilibrium solutions for the predator-prey system. So consider the exist system from lecture 1. Nonlinear system, we drew solutions to this before. Question, does the system have any solution pairs, f of t comma r of t, an ordered pair that we can graph in a rectangular coordinate system? By the way, in that last picture we just saw, it was a rectangular coordinate system, the ordinary kind of graph that you can make. which consists of two constant functions. Constant is what I mean by equilibrium. I can also use the word static, as I did before. And that's going to give us a parametric curve that itself is a constant function. And graphically, it's just a point in the phase plane. If so, find them. How do you do that? Well, essentially, you're looking for where you've got constant functions, so the derivatives are always going to be 0 for all t. That means you're looking for what coordinates for f and r give you 0 on the right-hand side. So you solve a system of algebra equations. This is a system of algebra equations that we can solve simultaneously. It's a nonlinear system, but by factoring out the f and the r, you can pretty easily solve it to get two answers, the point 0, 0 and the point 2, 1. 0, 0 for f and r, make these things 0, so you get a true equation. If r is 1 and f is 2, f is 2, r is 1, you get the point 2, 1, makes both of those 0. Are there any others? No. Because if f is 0 to make this one 0, r would be forced to be 0 because you get 2 minus 0 or 2 right there. So r would be forced to 0, and conversely that would happen the other way too. And if r is 1 to make this 0, you get a 1 there, which is not 0, so f would have to be 2 to make this part 0. You know, I said that fast. Might be worth watching again. Hand graph I was going to make here quick. Your phase plane, f is horizontal and r is vertical. Graph the rectangular coordinates here, these points based on these rectangular coordinates. Be those 2 points. Those are called equilibrium points or equilibrium solutions of the differential equation. They are constant functions as parametric curves. They stay where they are for all t. If you graph f and r as functions of time, where time is on the horizontal axis, their graph should be horizontal in that case. Really important comments I'm making here. Subtle things that if you don't get them, you'll be confused later. All right, our last few slides here. Oh boy, longer than I wanted it to be. I think I better keep going here though. Here's where we're going to illustrate change of coordinates. From rectangular to slanted or skew coordinates is the more official name. I'm going to go real fast here. I'm going to show you two graphs that are essentially graphs of the same equation, a linear equation. 4 times the first coordinate plus 5 times the second coordinate always equals 10. This graph is going to be a straight line in rectangular coordinates. In fact, here it is. Right, and you could find this by plotting some points or figuring out x and y intercepts. You also can solve for y as a function of x. It would be 10 minus 4x all over 5, 2 minus 4/5 x. So this has got a vertical intercept of 2 and a slope of negative 4/5. So that's an ordinary kind of graph, which you can graph by plotting points for this function. But now I'm also going to graph the same equation, but in a skew coordinate system. I'm going to keep the vertical axis still vertical, but I'm going to slant the horizontal axis and get this picture. And notice I'm labeling these axes differently with u and v. These would be my new variables, you might say, new labels. V essentially is the same as y, though I'm calling it something different. U is something different. It's a slanted axis, slanted at a 45-degree angle. And the same equation has a graph that looks different. It consists of different points in the given plane. You can maybe imagine these planes as being the same. I've just done a regular coordinate system there and this skew coordinate system here. And the points you would plot would be the same, but it gives you a different graph because the axis is slanted. This point, for example, right, let's say here, has a u coordinate of, go down to the u-axis, -1, -2, -3. U coordinate is -3. What is its v coordinate? Go over to the v-axis along the diagonal here. Crosses the v-axis at about 1, 2, 3, 4.5 or so. Those would be the uv coordinates, -3, 4.5 approximately for that point. And it is a different point in the plane than this point is. If you imagine this is the same plane, but just with different coordinate systems on them. It's still a straight line, though. because this is a linear change of coordinates essentially, does give you a different graph. I would encourage you to think about that more. Another example. Here's a nonlinear equation. First coordinate squared plus second coordinate equals 3. The graph, because of the square, is going to be a parabola. Here's the ordinary graph. It's the same as the graph of the function y equals 3 minus x squared. What if we graph the same equation, essentially, in different coordinates? We get this graph. It's not the same graph. Again, if you imagine both planes being the same, a point over there has got to correspond to a point over here if it's at the same location. We're just imposing different coordinate systems on these planes. Regular coordinate system there, skew coordinates here. It does give you different points, though it is still a parabola, amazingly enough. But the points are different. The labels of the points in this coordinate system would be the same as the labels of the points here. But these would be xy coordinates, and these would be uv coordinates. I forgot to mention that in the other one, in the other example. What if you graphed a linear equation in polar coordinates? This is the last slide. Have you heard of polar coordinates before? I hope you have. Should have had it in maybe pre-calc or calc at some point. It's going to be the same linear equation as a couple slides ago. 4 times the first coordinate plus 5 times the second coordinate equals 10. What's a polar coordinate system? Here it is, and there's the graph of this linear equation. It's not a straight line. Okay, well, let's talk about this to end the lecture here. This equation could be solved for r as a function of theta. R, in fact, would be 10 minus 4 theta over 5. That seems familiar. That's 2 minus 4/5 theta. Before we did y equals 2 minus 4/5 x. But I'm imagining r and theta as being polar coordinates of points now. Based on this polar graph paper you see here. I have the x and y axes in there for reference sake of a rectangular coordinate system. But the more important lines and curves to see here are these radial lines, these rays coming out from the origin, and these circles of different radii centered at the origin. The first point over here has polar coordinates r theta equal to about, well, r is the distance to the origin there, negative 4.5, I guess, pretty close. And theta, that's actually negative 3 radians. That's the angle here of a ray that would go through that point, like that. R theta would be negative 4.5, negative 3. Now this is a little confusing. We have r as a function of theta, but it is traditional when you write the ordered pair to write r first and theta second. So don't be confused by that. It's not what we usually do with x and y coordinate systems and functions of x. Put the r coordinate first, the theta coordinate second. This one is at theta equals 2 radians right there. Theta equals 1 radian, negative 2 radians, negative 1 radian, 0 radians, 1 radian, 2 radians, and this one is at 3 radians. However, you can, if it were 3 radians, you might think it should be over here, because 3 radians is almost pi. However, r becomes negative when theta is 3. You get 2 minus 12/5, which is negative. So when r is negative, you have to go in the opposite direction of the rays. The ray at an angle of 3 radians goes out this way. But since r is negative, you need to go along the opposite ray. Okay? So that's a real quick summary of some basics of polar coordinates. We will talk about that a bit more. That is nonlinear stuff. It's not really linear algebra, but it's worthwhile talking about to emphasize that equations and functions can be graphed to look differently depending on the coordinate system. Which coordinate system is best? It depends on the application. In all situations, the coordinate system to use depends on the application. We won't use polar coordinates much here. It's useful sometimes. We will talk about skew coordinates more often. That ends up being really useful. And I'll end by just saying it's useful for what I talked about in lecture 1 with eigenvalues and eigenvectors. Thanks for watching.